What is kinetics? In order to answer that question, let's take a look at these two images. Take a look at reaction A and reaction B and ask yourself, how are the processes similar and how are they different? Pause the tape to think about that before going forward. Hopefully you've noticed that the reactants and the products in both reaction A and reaction B are the same. And the other thing that is the same is the amount of time that the process took. But if you look at reaction A, the pictures imply that all three particles collide with each other simultaneously and instantly turn into the products. Whereas in reaction B, it looks like two of the particles smash into each other and form something else, and that something else smashes into the third particle that was present at the beginning and turns into the products. This is the sort of thing that kinetics is what people study. So kinetics actually studies two aspects of chemical reactions. The first is the rate. So the factors that allow us to predict how fast a reaction will go. And the second thing that kinetics is a study of the mechanism, or the nature and the order of the collisions that make a successful chemical reaction. So let's review what we know. Take a minute to think about what do you already know about how concentration, temperature, and surface area affect reaction rate. And now let's apply that to how do we make predictions about rates. We use something that's known as a rate law. And as you can see here, a rate law is a mathematical relationship between reaction rate and reactant concentration. So it's going to look like a mathematical formula that shows us how the reactant concentration mathematically affects the rate of a chemical reaction. Here's an example of a reaction. So we have sort of generic A and B are reacting to form generic products C and D. And this shows what the rate law might look like. So this is just a general format for rate laws. You'll see the word rate, and then an equal sign, and then a lowercase cursive k, and then brackets that have a reactant inside. So notice A is one of the reactants, and it will be raised to an exponent, and then you'll have brackets for the other reactant, and there will be an exponent there as well. So this lowercase k is called the rate constant. And as you can see here, it's constant for a particular reaction at a particular temperature. We're never going to have to calculate this. For our purposes, we're just going to always write a k into our rate laws. Then this bracket notation represents the concentration of, and that would be concentration measured in molarity. So this would be the concentration of reactant A and the concentration of reactant B. And then you'll see these exponents. And those are going to be experimentally determined integers. So they'll be whole numbers, and they're going to show us the mathematical relationship between rate and concentration. So here's an example of one. So you can see the chemical equation up here. So we have hydrogen and nitrogen monoxide reacting to form nitrogen and water. And this is the rate law for this reaction. So here's the word rate and the K, and then we have the concentration of one of the reactants raised to a power, which in this case is 1, so we don't write it in, times the concentration of the other reactant raised to a power, which in this case is 2. And when you show students this, right away, someone starts trying to look at the rate law and the balanced equation and figure out, where did those exponents come from? Or when I see the balanced equation, how will I know what the exponents are? And the answer is you won't. The exponents are experimentally determined. So a scientist in a lab somewhere has done experiments to figure out what those exponents are to show us the relationship between the concentration of each reactant and the rate. So if you take a look, this reaction is said to be first order with respect to H2 and second order with respect to NO. So just think about that for a minute. First order with H2 and second order with NO. So when we say the order with respect to a particular reactant, what do you think we're referring to? So hopefully you noticed first order refers to hydrogen's exponent and second order refers to nitrogen's exponent. So orders are really just the exponents in the rate law. Now this is the exact same reaction and exact same rate law, but this time it says the reaction is said to be third order overall. So what do you think we're referring to when we discuss the overall order in relation to the rate law? Hopefully you've noticed that 3 is what you get when you add 1 and 2. So the overall order is just the sum of the exponents in a rate law. So notice here it shows us the overall order is the sum of the orders. And again, this reaction is third order overall because 1 plus 2 gives us 3. It's first order with respect to hydrogen, and that tells us hydrogen's exponent is a 1. And it's second order with respect to NO, and that tells us NO's exponent is a 2. Here's a second example. So this is a different reaction. Iodine and acetone are reacting this time, and the information above the rate law tells us it's first order with respect to acetone and first order overall. And we're being asked to do a couple of things. First, write the rate law. Now we have the generic format in the center, but notice we have question marks where the exponents go. So our job is to use the information up here to figure out what would these exponents be. So that's the first thing we have to do. And then we're going to answer these two questions. What's the effect on the rate if the concentration of acetone is tripled? And what's the effect on the rate if the concentration of iodine is tripled? So pause the tape and think about that for just a minute, and then I'll explain what the correct answers are. Okay, hopefully you paused the tape. So this says first order with respect to acetone, and that means acetone's exponent should be a 1. So this question mark could be replaced with a 1. It also says first order overall, which means when we add the exponents, we should get 1, which means iodine's exponent has to be a 0. So now let's talk about what that means. When the exponent is a 1, that tells you whatever happens to the concentration, the same effect will be seen on the rate. If the exponent is a 0, essentially that means this concentration has no effect on the rate because anything raised to the 0 power is going to give us 1. So no matter what we do to the concentration, after we raise it to the 0 power, it's not going to impact the rate mathematically. So what's the effect on rate if the concentration of acetone triples? So if you can picture removing the formula for acetone and writing the number 3 in there, because 3 is what we use to represent triples, and then take 3 and raise it to the first power. So 3 to the first power would give us 3, and that means the rate will be 3 times as fast. And then here, what's the effect on the rate if the concentration of iodine is tripled? Well, if we replace iodine with the number 3 and raise it to the 0 power, we would get 1, and that means the rate will not change. Let's take a look at one more example. So this one is going to be sort of the backwards of what we just saw. So this time we have the decomposition of a compound turning into methane and carbon monoxide, and we have some information. When the concentration of the reactant is doubled, the rate is 4 times faster. And then if the concentration of the reactant is tripled, the rate is 9 times faster. So here's our generic format for the rate law, and we have to figure out what goes where the question mark is. So we need to write that rate law. And then we're going to answer these two questions. What's the order with respect to the reactant, and what's the overall order? So again, imagine that you could take the formula out of these brackets and replace it with the number 2 because it tells us that the concentration is doubled. So if this was a 2 and then the rate is 4 times faster. So this would be a 4. And then we ask ourselves, what's that exponent have to be to make that sentence mathematically true? Or you could use the second piece of information. If this was tripled and this goes 9 times as fast, what does this exponent have to be? So hopefully you see that the exponent would need to be a 2 in order to make this statement mathematically true. So the order with respect to CH3CHO is second order, and the overall order would also be 2 because it's the only exponent here in the rate law.